Okay, good day. This is Mr. McCulley, and this is Dual Enrollment Pre-Calculus lesson number 24, the fundamental identities. Let's get right to it. So today we're going to use trigonometric identities to evaluate trigonometric functions. We're going to use trigonometric identities to simplify trigonometric expressions, and we're going to use trigonometric identities to rewrite trigonometric expressions. Lots of trigonometrics in there. So before we get started, we certainly want to pull out your trig identity cheat sheet. We're going to be referring back to this a couple times during the lesson. I don't know why it does that. Okay. Especially these cofunction identities. And so you might want to take a look at that as we go through this. First, tips for simplifying trig expressions with trig identities. And again, none of these rules are hard, fast rules, nor should you necessarily take them in order, but certainly some things that we do often. If you ever get stuck, change everything into terms of sine and cosine. So use the let's go right back here. We'll still be using our fundamental identities, but if we use the quotient identities, we can take tangent, change it into terms of sine and cosine, secant, cosecant, and cotangent, turn it into terms of sine and cosine through the reciprocal identities. So that's one thing that you can do to help. We can use the Pythagorean identities. If you see something squared in it, you might want to take a look at or some trig function squared. You might want to take a look at the Pythagorean identities. And then some trig expressions can have greatest common factors, and see if you can factor out GCFs if that's possible, or use some other factoring method. So not a whole lot of new stuff, but there are some different types of questions that we're going to apply these possible topics. So my first example is use the given values to evaluate all 6 trig functions. Now we've done that before, and so we want to, I'm just going to rewrite them and fill in the ones I know. So sine x, cosine x, tangent x, cosecant x, secant x, and cotangent x. All right, so we know that cosecant is -2. We know that tangent is square root of 3 over 3. All right, and so let's see here. If I do the reciprocal identity, I can figure out that this thing will be 1 over 2, but it'll also be negative. The cotangent identity would be 3 over square root of 3, but we can't leave it like that because of we've got a radical in the denominator. So we're going to multiply by square root of 3 over square root of 3. That'll give us 3 square root of 3 over 3, which we will cancel out the 3's and just say it's square root of 3. And that's okay. The only thing we don't have is sine and secant. So we have to ask ourselves a few things. Where is our angle x? And usually we label angles with theta, but in this particular instance where they're labeling it with x, and that's okay. And so we have to ask ourselves, where is tangent positive and cosecant negative, or sine negative? Okay, well, sine is negative in the second and the third and the fourth quadrant, and tangent is positive in the first and third quadrant. So where they overlap is in this third quadrant. So if I start here and open, I'm here this way, and that is my angle measure x to here, x. I'm going to erase that though. I just wanted to show it to you. I'm going to erase it because I'm going to need some values here. So if the sine is equal to -1/2, all right. So that means this distance right here, oops, let's draw a little bit better picture there. This distance right here is -1/2. That means that this x value here has to be negative square root of 3 over 2. And again, I caution myself of saying that it is definitely -1/2. All we know is that the ratio to the opposite to the hypotenuse would be -1/2, and I'm putting it on the unit circle. So I mean, I really could put -1 there and 2 there. That would also be viable. So if that's true on the unit circle, we got a negative half. We would have to have negative square root of 3 over 2 for that to work. And then the tangent would be a half over square root of 3 over 2, which would give us this square root of 3 over 3, and it would be positive. And so for the cosine, we can put in 3 over 2, negative 3 over 2, and then the cosecant, I'm not going to do this work, but it would be 2 square root of 3 over 3, and that would also be negative. And those are our final answers for that. Next one says, do essentially the same thing. And even though we have a different identity here, this one actually turns out to be a little bit easier because we have a co-function identity right here. And so what we can do is if I go down to these co-function identities, I know that cosine of pi over 2 minus theta, or 90 minus theta, is going to be equal to the sine of theta. So I can take this one right here and rewrite this one as the sine of x equaling to 3 over 5. Now again, if I'm thinking about it as the opposite over the hypotenuse and the adjacent over the hypotenuse, well, all of these values can only be positive in the first quadrant. So we're talking about a fairly straightforward Pythagorean identity, or excuse me, Pythagorean triple triangle here, where the adjacent side was 4, the opposite side is 3, and the hypotenuse is 5. And this angle right here is x. And that makes finding the rest of those values fairly easy. If I have the sine of x, the cosine of x, the tangent of x, the cosecant of x, the secant of x, and the cotangent of x, we've got our 3 over 5, our 4 over 5. This one will be 3 over 4. And then I just do the reciprocals. So 5 over 3, 5 over 4, and 4 over 3. Those are our answers for that. All right, match the trig expression with a simplified form. So again, here we have some of these co-function identities, and just like in the last one where I said the sine of pi over 2 minus theta is the cosine of theta, and the cosine of pi over 2 minus theta is equal to the sine of theta. Well, this one here becomes cosine x, and this one here becomes sine x. And then if we use the quotient identity, we can reduce this quotient, cosine theta over sine theta, to cotangent theta, but since we're using x, we should say it's the cotangent of x. And there we have simplified. All right, well, moving on. Next example here, it says factor expression, then use the fundamental identities to simplify the expression. So now we have secant to the fourth theta and tangent to the fourth, secant to the fourth x and tangent to the fourth x. It's a difference. This is technically a difference of squares. And we learned that back in probably Algebra 1, that a squared minus b squared was a special factoring form, and it'd be a minus b times a plus b. And so we can factor this expression here into secant squared x minus tangent squared x, and then this thing here will be secant squared x plus tangent squared x. And so those two things are equal. We're factoring. And then let's see if we can use some fundamental identities here. And since we've got some squares, let's go down and take a look at the Pythagorean identities here. So if I subtract secant or tangent squared x from both sides, secant squared x minus tangent squared x would just be 1. So secant squared x minus tangent squared x, that's just a 1. And then we have secant squared x plus tangent squared x. And let's see, is there anything else I can do with that? Let's see. Using a similar one, secant squared x is equal to 1 plus tangent squared x. Let's do that. So I've got 1, and I've got 1 plus tangent squared x plus tangent squared x. I think the simplest I can do, because 1 times anything is just itself, I can collect my like terms, change this to 1 plus 2 tangent squared x. And I don't think I can simplify that any further. So I'm going to put a box around that and be done. Well, those are just some real simple examples. We can talk about more in class. If you have any questions, we will do there, but that's all I got. So the Star Wars fun fact of the day: Episode 4 was originally titled, or excuse me, Episode 6 was originally titled Revenge of the Jedi, but after a number of actual movie posters were created, George Lucas thought Revenge was very un-Jedi-like, so he changed the name to Return of the Jedi, and that is the fabulous movie that we now have. That's all I got today, folks. That's a short one. You should be excited. Have a good day. Bye.